right, welcome back everyone. So this week we're going to be covering the t-test, and we use our t-test for comparing two means. And you might be thinking, well, hey, we've already studied a t-test. And that's right. The t statistic or the t distribution, it's a general distribution, a general test statistic used in many different tests. So there's actually tons of t-tests you'll learn. I think in this class we'll cover 3 different ones, maybe 4. And then as you go on studying statistics, you'll learn about several more t-tests. So now we need to start being a little bit more specific in how we name these things. So really the t-tests we're looking at this week, we're looking at 2 different ones. Both of these t-tests are interested in comparing the means of 2 populations. So there's 2 basic experimental designs where you might be interested in doing this. And one design, which we can call the independent groups design, scores are collected from 2 separate groups of subjects, and then we're going to compare the mean. And so like the classic example there that I always think of is like, imagine you have some kind of like math intervention. So you have one variable that's nominal, categorical, two levels or 2 categories. You either got the intervention or you didn't. So you're in the treatment or control group. That's a binary variable, 1 or 0. And then we could have test scores. So then we compare the test scores of people who got the intervention to people who did not get the intervention. And if we actually randomize the assignment, that is, we conduct an experiment, then the mean difference in the 2 groups is actually a valid causal estimate. Causality is something that's very interesting, but it's also very tough to study. It's easy if we have experimental designs and we can randomly assign people, but not every research question you can rely on randomization. So the field of causal inference has developed a lot in the last 20 or 30 years, and we won't really be getting into causal inference, but I might be making occasional statements about causality because I do think that's a very important outcome to strive for in science. We want cause and effect relationships. We don't just want correlations, right? We want to really know that if I change X in some way, it's going to lead to some change in Y. And so independent groups design, the thing that you're going to be able to identify is we have 2 separate groups. So here in the example I gave, we had a treatment and control. They had nothing to do with each other, right? They didn't like go and help each other in the test and all of that. So complete independence in the 2 groups. A second type of t-test we're going to learn is really when you have a dependent groups design. And in this one, there's 2 different types of designs you'll see that are common in the literatures, depending on what field you're in, that use this type of design. The first is what we can call repeated measures. So you could take that study I just talked about, and instead of giving it to 2 different groups of people, I could give it to a pre and post intervention test to the same subjects. So person 1 is in both pre and post test. Person 2 is in pre and post, and I basically have a set of paired test scores, right? So person 1, if they're really smart, they're going to tend to do well on both tests. If person 2 is more average or maybe not as smart, they're going to be a lower test score than person 1 in general. So that we call repeated measures, and we have 2 scores from the same person. So each person contributes 2 scores in that design. Another type of design is when you have basically paired or matched subjects. So for example, you might do this if you're concerned that pre-existing math ability is going to be something to control for. I could give a pre-test, and then I could take the 2 strongest students, put one in the treatment, one in the control. Take the next pair of strongest students, separate them randomly, the next pair, separate them randomly. So when I do that, I have different people in each group, but the groups are not independent, right? Because I actually am basically balancing the groups based on matched pairs, where I put the 2 smartest in opposite groups, and then I go down to the next pair, and I'm randomly assigning within the pairs. And so we do that if you want to hold something constant like pre-existing math ability. If I give that pretest, that allows us to create equivalent groups. So there's other examples, like for example, if you do an intervention on helping husband and wives in a marriage, like the husband and wife know each other and they're in the same marriage, right? So they're going to have a lot of the same correlated observations and measures on like how happy they are, or fulfilled they are in their marriage. So there, if you have a husband and wife, you have two scores from the same pair, and those scores are correlated again. So the scores are dependent up on one another. So, as we get to more examples, we'll talk about these types of designs versus independence. And I think after you see a few examples, it'll be a little bit clearer on the different types of designs. Now, if we're in the independent groups design, we're going to use the two-group independent samples t-test. So this is probably the most common t-test you're going to see out there. The independent samples t-test. There's various names for it. I think this is pretty much the most common. And then we have the dependent samples t-test. I actually think the book uses confusing names that are not conventional for these different tests. So on all my lecture notes, on the exam and everything, we're going to use the definitions as stated in these lecture notes. So for example, the book uses like pooled sample t-test. That's a less common name. I don't recall seeing that anywhere outside of the book. But like the dependent samples t-test, we can call the paired samples t-test. And that's actually what SPSS calls it. And it makes sense because you're pairing the scores. And again, we'll see an example of this shortly. And then, so I would say the dependent samples or the paired samples t-test is what most people call this other one. And again, the two-group independent samples t-test, the independent samples t-test, or the independent groups t-test, some variation of that is really what people use to refer to this type of t-test. So that's what we're going to be learning today, is how to conduct these different types of t-tests. Now, before I jump in, I want to make a note that before our midterm, we focused on what I like to call, and others too, not just me, univariate statistics. And what this means is that we looked at statistical techniques for describing a single variable and its distribution and behavior. So the word uni, of course, meaning one, variate, variable, univariate. These are statistical techniques that describe a single variable. This week, we're going to be focusing on bivariate techniques. And the word bivariate, like you can probably guess, means we're going to be comparing two variables. So far, we've taken things like the average income, the gender distribution, the income distribution, whether you're in treatment or control. We've looked at variables alone. We're now going to start looking at how they are associated, how they correlate with each other. And we're going to be using techniques to test whether, two variables are statistically related or not. And a lot of research questions, in fact, most research questions aren't just interested in a single variable. So now we're entering the world where like these are the stuff we're learning in the next few weeks, where you're going to be able to really start applying this to the main research questions you have. And every research project you ever conduct, you have to do stuff like look at the mean, look at the standard deviations, min, max, the range. You're going to take your ordinal and nominal variables, which are both categorical, and you're going to create tabular summaries, frequencies and relative frequencies, or percentages, like most of us prefer to call them. So all of that is still useful, and you'll do that on every project, but that doesn't really allow us to answer most research questions. For example, is there a gender difference in test scores for some math test, right? There's two variables, gender, and if we simplify the world and just say there's two genders for now, male and female, I have a binary categorical variable, and then I have test score. That's going to be some kind of numeric variable. Ideally, it has a continuous and normal distribution, which is an assumption of these tests, like we'll talk about in a little bit. Okay, so I've set the stage for us to jump into learning about the independent samples t-test. So there is going to be some math here, but as long as you can multiply, add, divide, subtract, square root, take the square term, that's it. So there are a few formulas we're going to have to learn to get this type of t-test done correctly. But with repetition and a few examples, you'll see the math's never going to change on you. So, definitely study the examples in this notes, and then from the homework to prepare for the final, definitely make sure you can do the independent samples t-test that we've given, because on your final exam, there will be similar style of question. I'm not going to throw something crazy. It's going to really follow the lecture and the homework examples for these. So yes, there's a lot of calculations here. We really haven't done a whole lot of calculation to this point. We've done things like compute the mean and standard deviation. This week, we're going to be using all that we learned. We have to know how to do that to start getting into these t-tests. So let's start with another example. I gave an example earlier, but let's look at a second example. Say we want to compare males and females for an importance rating on a particular social issue or problem, like healthcare reform. So you could measure healthcare reform attitudes on a 1 to 9 point scale. And then you could have another variable, gender, male and female. And you might want to know, is there a difference between the ratings that males and females are giving? So that's a common type of research question. Again, we're interested in comparing two variables. So how we're going to do this is we're going to pick a random sample of males and a random sample of females. And we're going to also gather their ratings perceptions. Now, the groups need to be truly independent. We'll get to the assumptions later, but just to say, like, the males should not know one another and the women should not know one another. Now, you do have challenges like, what if you're in the same class? They're technically not independent. I don't want to talk too much about that, but the important thing is that, like, on a math test, it's not knowing each other that matters. It's that person one sitting next to person two, they're not like cheating, they're not giving each other information. Now, they may have just like an incredible teacher and they all may be like very good at math for that reason. But when we say independence, we're really talking about like your scores should be independent of the next person's scores. Now, there is going to be never fully, if you're in the same classroom, there's never going to be full independence. And so there are t-tests that deal with dependence like this. Which we're not going to cover. We cover the dependent t-test, but there's different iterations of this thing for like that type of independence assumption being violated. So beyond the scope of this class, but I just want to say we're making assumptions that, you know, when we say independent, we're really talking about the scores should be independent. You know, they may see each other passing in and out of the room, but as long as that's not going to mess with our measure of the test score, that's fine. So the two groups should be independent, and, you know, ideally they don't know each other. You know, if they do know each other, then you need to think about a little bit more about, like, you know, is this subject giving all the answers to someone else? Then that's going to break the independence assumption. So again, just kind of use common sense on whether the independence is tenable or not. You know, the real world is messy when we get to actual research. So in this type of design, then we're going to be dealing with 6 quantities. First of all, we're going to have these sample sizes of the two different groups, and we're going to denote that with N1 and N2. Additionally, we're going to need the mean, the sample mean, and the sample standard deviation of both groups. So because we have N sample size, X bar the mean, and little s standard deviation, we have that for two groups. So on these types of problems, you're dealing with 6 quantities, which a homework problem will give you. So that's how you can identify, one of the ways you can identify that you're dealing with an independent samples t-test. So that's an example of how we set these problems up. Now, how do we actually conduct the test? Well, we learned hypothesis testing recently, and the good news is hypothesis testing tends to say pretty similar. And as you test different types of hypotheses, there are differences. Yes, but there's a lot of similarity, and particularly the first 2 steps really never change. So the first step is to identify the null and alternatives, and depending on the type of test you're doing, these can be different. But you can see here, there's different ways to write these null and alternatives. So what we're literally interested in comparing, we don't care about the sample means being different. They're always going to be different. We care about the population means being different. And so what that means is we can basically write these hypotheses in a few different ways. We can write the null hypothesis as mu1 minus mu2 equals 0. So that's saying there's no difference in the means. They're the same. They're consistent with one another. And it's funny, so this is the two-weighted side. I'm going to stay focused on this. And then the alternative is just, as usual, not equal. So if you have a two-sided hypothesis, very extreme positive or negative numbers suggest that the null is not credible. So our rejection region on a two-sided, again, like we studied before the test, it's in the tails of the distribution. Now, a one-sided test could be, look, the nulls are all the same, right? So what's different in the one-sided is now we're saying mu1 is greater than mu2. Here we're saying mu1 is less than mu2. So again, it's the same way of directional or one-sided versus two-sided. That stuff we learned before the midterm, and hopefully you're feeling comfortable with that. And we'll again do some practice problems to see these examples. Now we're going to determine alpha as our step 2. This is consistent with what we learned before the midterm. And our critical test statistic is going to be T, and the degrees of freedom are down here, N1 plus N2 minus 2. That's clarified right here. And then we have alpha. Again, just like we have before, every time you take a critical test statistic, you need to know what level of significance that you're testing it at. So steps 1 and 2 should feel familiar, although our null alternatives are written a little bit different because we're comparing two means now. And then step 3, this is where all the math comes in for us. We're going to gather the 6 quantities we talked about before, and then we're going to compute the observed test statistic. And there are 3 steps for computing it. And my strong suggestion is you compute it in exactly this order given in the notes. So the first thing we need to compute is called the pooled standard deviation. We denote that with S sub p, or SP. And you can see it's equal to the square root of n1 minus 1 times the variance of group 1 plus n2 minus 1 times the variance of group 2. And the denominator is just n1 plus n2 minus 2. So we'll do examples with that, but really all we're doing is multiplying, subtracting, adding, square rooting. Should not be anything too crazy in there for us that we can't handle at this point in the semester. Finally, we also need the standard error of the difference. We can denote that with little s subscript x bar 1 minus x bar 2. And notice that you need SP before you compute the standard error of the difference. So that's why I recommend you go in this order always. And then you're going to take SP and multiply it by the square root of 1 over n1 plus 1 over n2. And then finally, our observed test statistic is x bar 1 minus x bar 2 minus, we always put the null value there. Now notice the null value, x mu1 minus mu2 is 0. This is basically just not even going to be there. It's because that's, if you plug in the null value, that's going to be 0, minus 0 is nothing. So really what this often reduces to is x bar 1 minus x bar 2. That is the mean difference in the numerator divided by the standard error of the mean difference in the denominator. Finally, we take our observed test statistic, and as we've been doing, we compare it to the rejection region. Or you get the exact p-value, or you construct a confidence interval. And you see if 0 is in that confidence interval. So we've learned 3 different ways to conduct hypotheses tests. We're going to jump into SPSS in a little bit in this lecture, and we will see there that that's always going to give us the p-value approach. When we do these as a class, I typically prefer to just do the rejection region approach. So again, you can do either approach, they're going to give you the same answer, and we'll see examples of this soon. So again, comparing observed test statistic to the critical, right here, critical test statistic. And the critical test statistic, that's what makes the rejection region, right? It's anything far away from the middle to the right or left, depending on, the problem and research question you're trying to answer. Okay, so let's look at an example. This comes from a textbook, Mendenhall, Beaver, and Beaver. And notice they're going to give us the 6 quantities that we need. So they've given us the sample sizes, the means, they've given us the variances. So we should know by now that we can get the standard deviation by square rooting 4.8. So if you go and square root 4.8, you'll get 2.19. If you square root 5.9, you will get 2.4. And what we want to do here is test at the 0.01 level to see if the two means are equal. So we're going to go through our first step, and I will, looks like step 1's repeated twice. So I will delete the additional step 1 because we only needed to see it once. The first thing we're going to do is we're going to set up the null and alternative, and you can see here, it's just really copying from what it was above. We're looking to see if the mean difference between the two groups is 0 or if it's not, right? That's what we want to test. The problem gave us alpha at 0.01, so we start there. And it asks if the two populations are equal or not. So this is not a one-directional test, it's 2 directions. So that means we need to divide alpha over 2 because we are going to split the type 1 error in the two tails. So let me see if I can draw this for us. So the two-tailed test, remember, the reason we do this, our t is always centered over 0. I've got 0.005 area there. I've got 0.005 area there. So that's why this is basically alpha over 2. This is alpha over 2. And when you add those, right, you get your alpha of 0.01. So in a two-tailed test, that's literally what we're doing. We're splitting the type 1 error rate into two tails because, again, we're just interested if it's different or not. So very large positive or very large negative numbers away from 0 will suggest the null hypothesis is not credible. So we should feel comfortable with the two-tailed versus one-tailed, and why we're dividing it by 2 there. Now, secondly, we've got the degrees of freedom. So the sample size of group 1 is 16 plus 13, give us 29, and then we got a minus 2. So 27 degrees of freedom. So look at this. I'm going to clear. So I want to go find the critical test statistics. So how do I do that? Well, it's just as we've done in the past. We are going to go to our t-table. We're looking for 27 degrees of freedom and an alpha of 0.005. So I come down here to alpha, the df of 27, and then I'm in the last column here, so 2.771. So that's how we get that number. And if I were to pull that back in the picture, what I'm basically saying then is that negative 2.771 and remember it's symmetrical, that is marking my rejection region. So if I have a t observed, the absolute value of which is greater than the absolute value of t crit, I'm going to have to reject this null hypothesis. So we know t crit, let's go get t observed. And there is, again, 3 steps. We start with SP, and I'm just plugging these numbers in. I don't really have much to show you other than just plugging them in. If you are having trouble getting 2.3, let me know. But you should be able to do this in Excel. You can use a calculator. There's various softwares that you can use. You should not be doing this by hand. And then we're going to use that 2.3 in our equation for the standard error of the mean difference to get 0.859. That standard error of the mean difference is in the denominator. Now notice mu1 minus mu2, as shown in the null, we need to shut that down, and it's 0. It's pretty much always going to 0 out. So really, we're just dealing with the mean difference in the numerator, which is 2.4. We're going to divide that by 0.859, and we get 2.795. Now, 2.795, that is in the rejection region, right? So, sorry, they have updated zoom. Trying to figure out. So 2.795, it literally is like right here. So just barely, we're going to reject the null hypothesis and conclude that the two population means differ. So that's it. That is the math that we're going to have to do. This is some of the most difficult math we'll cover all semester. So if you're feeling comfortable with this, good. If you're not, that's okay. You'll have time to practice, and definitely come to office hours if you need additional help. Okay, so there's a second example. I'm going to let you look at that on your own, but nothing really changes. It's the same kind of thing. I want to talk briefly about the assumptions. So I'm going to be brief here. The assumptions are essential. Every time you conduct a hypothesis test, you need to know the assumptions that underlie that test, because if you violate the assumptions, it means that our hypothesis test is perhaps not valid. And we can use almost always, there's another test that just provides a valid answer. So the first assumption is you need two variables to conduct this test. It's a bivariate statistical procedure. So one variable is going to be numeric. And usually this is the dependent variable, but it's not always. You can have the IV be numeric and the dependent variable be a grouping variable. Like in medicine, they do that. They'll have some continuous thing like blood pressure, and then they'll have their dependent variable or outcome variable will be has disease, does not have disease. So that's a 1 or 0. And so there, it doesn't matter what the IV and DV are. What really matters is that there's a numeric, ideally continuously normally distributed numeric variable, and a binary categorical variable. That's going to be the second type of variable. We usually call this the grouping variable. So getting back to the example before, you want to know the difference in test scores between males and females. Well, gender is the grouping variable. Test scores is the numeric, hopefully continuous and normally distributed variable. So first assumption covered. You need to have two variables. Second assumption, the numeric variable should be normally distributed. Now, should be. Doesn't say has to be, it says should be. In the real world, you never have perfectly normally distributed data. The normal distribution is a theoretical distribution, that bell-shaped curve. It's perfectly symmetrical. You don't see that in practice. You'll see things that look almost symmetrical. They look normal-ish. If it looks normal-ish, you're good to go. The reason I say that is because it's robust to violations of normality. So you have to have like really severe skew, or there has to be like a bimodal thing. Like it has to look like kind of like a crazy distribution, if you will, before you need to really panic. And if you don't have a normal distribution, again, depending on what exactly the violation is, there's other statistical tests which are beyond the scope of our class that can get around this. Now, one thing, I'm not going to test you on it, but you should be aware that if we break the normality assumption, you can go to this thing called a non-parametric test, which is the Mann-Whitney U test. The textbook covers this. I'm not going to cover it in details, but again, if the normality is the assumption you're breaking, you can just go and use this test, and it's like pretty easy to do in SPSS. So how do you assess normality? Well, I'm going to say you make a histogram. Some people there's actually a statistical test. I think one's called like the Shapiro-Wilks test that will go test this. I don't like that stuff. I just want to make a histogram and look at it. And if it's anything even close to normal, then I just go on. So I prefer to assess normality visually, and I suggest you do the same. It's just the easiest thing to do. You should always be looking at visual techniques for your data. Now, a really important assumption here is the homogeneity of variance between the two groups. So I have group 1, I have group 2. They need to have similar variances or standard deviations. So the rule of thumb that we're going to use is that the standard deviations, if one is 5 and the other is 7, good. If one is 15 and one is 17, good. We're going to use a ratio of 2 to 1 as a rule of thumb. There are statistical tests for this, and we'll look at one in SPSS in a minute called the Levene's test. But if you want to just kind of have a quick kind of rule of thumb, 2 to 1 means standard deviations, and that's I've seen Dr. Corder use this rule. I've seen Dr. Keller use this rule. So statisticians out there subscribe to this rule. It's subjective though, so probably if you're testing the homogeneity of variance assumption, it's best to do with the Levene's test, which I'll show you in a second how to do that. If we call this HOV, homogeneity of variance, if that assumption is broken, then we just use a different t-test called Welch's t-test. We'll see it in SPSS done. It's like, again, like almost the same thing, just slightly different. And you're not expected to know the math of the Welch test, although it is right here. I'm not going to cover that, but you just need to know that if you break the HOV assumption, that's what you do. Finally, independence. I've talked about this. It's pretty much an assumption of all tests we learned this semester. So scores from one person should not be influencing the scores of another person. If you're in the same school and your school's really good and you have really good teachers, in practice, technically it might be violated, but if we're really just focused on making generalizations about the population at that school, then usually we can just say independent, unless they're all like working together on the group or sharing answers. That would be an issue. Them knowing each other isn't necessarily an issue. But this just takes some judgment, but it's a pretty easy assumption to get around and understand whether it's broken or not. It's usually satisfied. So before I jump to SPSS, I do want to talk about one thing real quick, and that is confidence intervals. We can create confidence intervals. So, we've used confidence intervals for two reasons in the past. One is to give an interval estimation. Like if I am forecasting the returns of a stock and I give you a confidence interval of, well, let's say the 5% returns on average. If one has a confidence interval from -5 to +15%, there's wild variability. I don't feel very good about that estimate. If another has a similar confidence interval of say 95% confidence interval, which goes from 4 to 6%, that's the stock I want to invest in. So interval estimation conveys how accurate our predictions are. The second reason we conduct confidence intervals is because they help us do a hypothesis test. So basically, the confidence interval, it's the same form as other confidence intervals we studied. The statistic we're interested in is the mean difference. So that is the estimate of the mean difference is right here. And then I add and subtract. We're making, again, we call this thing the margin of error, these two things multiplied, the t-crit and the standard error of that statistic. We call those the margin of error. And this is just a t-crit. We find that in the same way as above. And then the standard error of the mean, we calculate, again, with the same formulas. So really, if you're doing confidence intervals, there's not much more to learn. You just have to remember like, hey, this is the formula for it. It's basically the same formula that we've been using. The difference is that we have a different statistic. We're creating a confidence interval for a different statistic, but the general formula for all confidence intervals are statistic of interest plus and minus the margin of error. And the margin of error always has two things in it, the crit and then the standard error of that statistic. So there's an example here, and you can see here 2.2 plus or minus 2.38. So notice 0 is in that confidence interval. So we could not claim that the population means mu1 and mu2 are statistically different, if that's what you were trying to do. So now what I'm going to do is I'm going to jump to SPSS and quickly go through an example of how to do an independence t-test in SPSS. So on Canvas, if you go to the module and you come into, let me show you where this is. if I click here, comparing the means of two populations, there's this stuff down here that's SPSS, and look, you can come in, you can download these files. I've already got them on my computer, so I don't need to download them. But these are going to allow you to replicate what we're about to see in this video. And then I also have independent and dependent t-test stuff down here. So the first independent t-test we're going to go perform. This is basically how we report the results in APA. So let's go do that. So to perform this test, we need the data set. The data set has a .sav, that's SPSS file extension for data sets. And it's called t-test independent groups, example 1. So I'm going to go to my t-test SPSS example 1. And remember, we talked about how there is a, one of the assumptions of the t-test is you need two variables. So you should not be surprised. I've got a grouping variable, experimental or control group. And then I've got, that's my categorical variable. And then here I've got the score variable. So remember, before the midterm, I posted instructions on how to import data and a few basic things about SPSS. You're going to want to make sure you've watched all those videos before you're going to be fully up to speed and following me and doing some of these procedures. So let's say that I want to get some descriptive statistics. I can just right click on this column and I can right click descriptive statistics. I've got to navigate to my output window. And so you can see here, it's giving me the mode. There's 18 observations. Gives me the range, the minimum, the maximum. And then, well, that's funny. So what it actually, so it basically is giving me a tabular summary of the data. And that's because we stored the data. You see this little thing, SPSS recognizes that as categorical data. So if I actually come here, you have to change this on your computer too. It says type numeric, but measure nominal. That's a contradiction, right? Numeric scale is what it should be. Now, if I go back and hit descriptive statistics, it will give me like the mean, the median, the standard deviation. So look, standard deviation is 1.8, the mean is 5.6. I would say there's a decent amount of variability here, but there's not like a whole bunch. If like the standard deviation was 10 and the mean is 5, when the standard deviation is way bigger than the mean, then you know it's really a story of dispersion and spread in the data. But here, you know, there's decent variation. If I draw this distribution, it might look like this, 5.6. And then, you know, I'll probably have some down at 3, have some down at 8, but there's not going to be a whole many, and you can see the actual data there. So I just basically constructed that little shape really quickly. Now, we only have 18 observations, so it's not going to look very normal, right? When you have small sample sizes, these distributions will never look fully normal. When you have like 1,000, oftentimes you'll see it's like almost a perfect normal distribution. You know, there's always jaggedness, but with 18, you shouldn't graph this and be expecting to look normal. It's a hard thing with 18 through any measures, not even just like if you do statistical tests, like the Shapiro-Wilks test, that's not going to be very reliable for basically the reason being there's not enough statistical power. So it's just never going to reject the null. In any case, when you have 18, it's hard to assess the normality assumption, but the t-test is robust to violations of normality, so it's not a hugely important thing, I would say. Oops, let me share my screen. Sorry about that. Okay, so I've got basic data there. Now, if I want to conduct this t-test, so I'm going to go back to my data. I always like to see my data. I want to basically, I can do this in the Analyze menu. So I go to Analyze. Sorry, my zoom bar is in the way. I go to Analyze, Compare Means, and we're doing an independent samples t-test. So I'm going to click there. And this is already, because I just did it. So what I need to do now is I need to take the test variable is going to be the numeric variable. That's score for us. And then the grouping variable is going to be, well, we've called it group, so that should be easy for you to find. And then for some reason, you have to come in and define, like you can see I have an E and C here. I guess the idea being if there was a third category there that I could just, instead of like I could just pick the two groups this way. Because remember, the t-test assumes there's a categorical variable if there's only two categories. If I had like a third group, like experimental 2, I could only compare E1 to E. I could only compare E1 to C, or C to E2, right? There are procedures that allow you, they're called ANOVA, which we'll learn in a few weeks, that'll allow you to have many means you can compare, but we'll learn those in a few weeks. So I hit continue, and now I hit OK, and it's going to pop up some information for me. So the mean in the experimental group is 6.5. That's greater than 4.5. Well, that's good news for us. Maybe my experiment worked. The question is it statistically significant? That's really what we're going to care about. It's nice to see a difference, but is it statistically meaningful? Well, that's why we conduct the t-test. It'll tell us if it's statistically significant. So remember we said that one of the assumptions of the t-test was homogeneity of variance. So in SPSS, it's just going to automatically conduct Levene's test for you, which will test the HOV assumption. And you see it's not significant. So remember, significance is a p-value below 0.05. This is nowhere close to 0.05. It's like highly non-significant. So we're okay to be in the first row here where we have equal variances assumed. So I'm looking at the first row of data, and I've got a t statistic of 2.650, a DF of 16. Look, it gives me one and two-sided p-values. So here we were doing a two-sided p-value. So that's 0.017. And I guess we didn't really have a research question, but the default is two-sided. And then the mean difference, 6.5 minus 4.5 is 2. I have the standard error. So the standard error of the difference, this is, if I go back to our notes, it's this quantity right here, standard error of the difference. And then finally, it even gives us a confidence interval at the end. So basically, what I'm going to do is how I look at this table. I know there's a whole lot. You only need to look at a few places, though. First, Levene's test. Okay, not significant. So I'm assuming equality of variances. I'm in the first row. Second thing I do, if I'm in a two-sided situation, I just go look at my p-value. 0.017, that's lower than 0.05. Therefore, we reject the null, and there is a statistical association between the treatment group and test scores, such that the treatment group actually has higher scores than the control group. Now, how do we report this in APA format? Well, this is how we might say it. We first conduct some descriptive statistics. We have N1 for the experimental group, has a mean of 6.5, standard deviation. For the control group, we have 8 individuals. The mean is only 4.5 there. So notice there's a 2.0 difference in the means. Notice how we also give the SD. And then finally, a t-test for independence group showed difference at the 0.05 level between the means of the two groups. So in APA, we put the test statistic, T. So this case, the test statistic has a T distribution, so that's why it's a T statistic. We put the degrees of freedom in the parentheses. The degrees of freedom are N1 plus N2 minus 2, so that's going to be 10 plus 8, 18, minus 2 to get us 16. 2.650, that came straight from my output. Degrees of freedom, it also calculated at 16 for us. P-value 0.017. So that's how we conduct independent samples t-tests in SPSS. And you can imagine, look, if I have this data, I might be able to like kind of eyeball it and say like, yeah, you know, the experimental looks a little higher, but imagine if you have thousands of rows, right? Then doing this, it's not going to take any more time than if I had 20 rows. So, you know, often in this class, we have really small examples, but you do want to think like what happens when I have hundreds of rows or thousands of rows. These tests are very efficient to do, very easy to do, and they never really change how you do them and interpret them. So, you know, you'll get good at them over time. Now, with that said, we are going to turn the page here and start talking about the dependent samples t-tests. So the first type of t-test is called independent samples t-test. And it's called that because we have two groups and they're independent of each other. They don't know each other. I have test score of group 1, test score of group 2, and they're independent. That is not the case here, where test score 1 and test score 2 are dependent. That is, they depend on each other. They're correlated. And as we said earlier, there's two types of designs you'll see here, repeated measures design. So imagine you have a French achievement test before and after a 1-week immersion course. So you have pre and post scores of the same people. Each person takes 2 tests, pre and post, which means their test score on the first occasion is probably correlated with their test score on the second, right? They're not just going to go lose all their prior French ability that they had in the pre-test, right? So if they're already scoring higher pre-test, they'll generally score higher on the post. The question is, are their scores statistically higher on that second test or not? There's another type of test where you can match the subjects. So give them a pre-test, take the 2 highest individuals, assign one to curriculum A, one to curriculum B, then you take the next 2. And you do this so that you know you have equivalence in abilities, pre-existing geometry abilities in this problem. So they're different people in the groups, but the scores of the are still correlated or dependent upon one another because you've intentionally placed the top performers, then the second, third, fourth, you're intentionally splitting them up in blocks, right? So this leads to a correlation of scores, and we'll learn about correlation in the near future. And so this second type of design is called matched groups design. So why, sometimes an independent or dependent is just kind of the natural decision based on your research question, but sometimes you have a choice, and so it's important to talk about the advantages or disadvantages of each. And so in the repeated measures design, the nice thing is, like, let's say I have that French pre and post test. Because the outcome that I'm interested in is whether my post test goes up, like, I'm taking the same person and comparing the difference in their test scores. That means things like their age, their gender, their underlying IQ, the amount of French they spoke growing up, everything is held constant because I'm comparing a person to themselves, right? So when you have a repeated measures design, this is true that each person serves as their own control, and that's a pretty nice thing. That's not necessarily true if you do the matched groups design because they're still different individuals. And so, if the top 2 performers are one's female, one's male, well, you don't have, right? They're matched on their ability, which is probably the most important thing to keep constant in the 2 groups, but they're different in gender. So not perfect equivalence that you're able to create through the match group design, but you're able to create equivalence on the most important variables like pre-existing geometry scores in the example we give above. Another advantage is that each subject can contribute 2 pieces of data. Again, this is in the repeated measures design more than, well, it's not true in the matched groups design. You still need 2 separate groups of people. So in the repeated measures design, there are some nice advantages here because each person gives you 2 scores. So if you only have 30 people, you actually turn that into 60 data points, which is nice. To recruit fewer people. There are some disadvantages. There can be memory or practice effects. If they saw a pre-test, they might be better at the post-test just because they've had time to practice on the way you format it and ask questions. So how do you really know that your intervention increased their scores from a causal point of view? Well, you don't. So, you get around that through like randomly assigning test subjects to different treatment controls, and then you do an independent samples t-test. So there are some disadvantages here too. Now the procedure is going to look really similar to before. So we start with our null and alternative. These are the same as before. Now we can also write, we'll commonly do this, where mu1 minus mu2 equals mu d. And this is called the difference parameter. And we can also write that if we're dealing with samples. this is the difference parameter. So remember, there's a population parameter and a statistical estimate of that parameter. So D bar estimates mu D. So D bar you're going to see showing up down here in our formulas. And so again, D bar is the sample difference statistic. We call it the difference score, the difference statistic. And so you can write, because the difference is just X bar, sorry, if I go into the population value where how we write nulls and alternatives, mu1 minus mu2 is the difference. So I can just kind of substitute in everywhere, right? It's all we're doing. You can write the null alternative either way that you prefer. And then step 2 doesn't change. We need to get alpha that's going to be given in the problem. If it's not given in the problem, you always assume it's 0.05. And then you need to do the t-crit to form your rejection regions. Now the degrees of freedom are different here because we don't have two separate groups of people where there's N1 and N2 floating around. There's pairs of subjects. We'll see what the data looks like for a dependent samples test shortly, but there's only one sample size, right? If I have 30 pairs, that means I have 30 observations of pre and post. There's no longer N1 and N2 because there's just N1 equals N2 here. There's only an N, right? If you're missing a pre-test from someone or you're missing a post-test, you have to throw that data away. So you need 2 scores per matched pair. And finally, we come down to 3 and 4, where we actually conduct the test. We do our T observed. So the math is a lot more straightforward here. So as usual, this is usually going to be 0. So really, remember D bar, this needs to have a bar on it. So D bar is the difference of, oh, you know what? No, it does not, because that's for a single person. So D bar, I just wrote it a second ago, is the difference of the two means, right? So you can write this T observed a different way. You can write this as X1 bar minus X2 bar over the standard error of D bar, right? And then the minus mu is just going to zero out pretty much most, if not every time in this class at least, and pretty much outside of this class too. But you can test whether the difference is 1 and then it wouldn't zero out, but that's not something you really see people do. And finally, once we have our T observed, we are going to see if it lies in the rejection region or not. It's our test statistic, and we'll make the same decisions as usual. If it's in the rejection region, we reject the null, and we would say that there is a difference in the pre and post or the matched pairs, depending on what the research design in question is. Okay. So let's look at an example. So here, how we set this up, we have 7 pilot subjects and an education intervention study. We have pre and post for each. So look, how you're going to be able to identify these types of questions is you're going to have some data like this. You're going to have subjects. Here we have 7. They each have 2 scores. And they don't have to be the same person, right? In a repeated measures design, they're the same person. But remember, they can be matched based on, they use a match design, and there's 7 pairs of students, right? But the thing is, there's not N1 and N2. There's just N. We just have 7. So there's 7 rows in our data set. Each row has 2 scores, a pre and post, or time 1, time 2. It depends on the design. And then finally, we're going to calculate the difference for each person. So this is going to be 28 minus 2. That gives us 6. We have 19 minus 1 or -1, 26 minus 3, etc. Right? And then we're going to take the average. So D bar, that's how we notate that. And then what we're going to do now is we're going to take the difference of d minus d bar. So 6 minus 2.714 is 3.29. Then we have -1 minus 2.71. That gives us -3.71, etc. We're going to go down. We're going to form that column. And you'll know you've done it correctly if they sum to 0. They have to mathematically sum to 0, so you can kind of check yourself there. And then finally, we're going to square it. So 3.29 squared is 10.8, -3.7, etc. And then we're going to basically, so remember the variance is going to be calculated as in the same way as before. So if I take this 27.4 and I multiply it, divide it by 6, I'm going to get like 4.5. And then the standard deviation, this is the variance. The standard deviation, of course, is the square root of the variance. So the square root of 4.5 is 2.1. So we should feel comfortable getting all the values in this test, in this table. And now we're going to be just plugging our stuff in. So d bar, so hold on, let's start with the standard error, the mean difference. So that's going to be equal to the standard, the standard deviation of the different scores, which is 2.14, and then divided by the square root of 7. So remember when we studied the sampling distribution, the sample mean, the x bar, it had a standard error that was equal to the standard deviation divided by square root of n. Right, so that actually is the same thing going on there. What we're basically doing in this dependent samples t-test is we're basically turning this into a one sample t-test. It's literally the same thing as a one sample t-test that we learned before the midterm. And we're doing our one sample t-test on this quantity. And we're just saying, is the difference score equal to 0 or not? If it's not, it suggests there's been a difference in the pre versus post test. And so that's why you'll see the math here is actually the same as the one sample t-test we learned before the exam, though because we're dealing with difference of means, the notation is a little bit different, d bar. And then finally, once we have S sub d bar, that's our denominator in the test statistic. And then we have 2.25. So 2.25 is going to be, hold on a second. There might be a mistake in these notes. 2.25. This should say, so I don't know which number is correct. I actually would need to verify. I'll post this in the notes. But actually, let me do this. I can verify it really quickly. So 6, -1. 6, -1. 3.224. And then 3. Oops. So the average is 2.714. So yeah, this number, this should just say 2.714. So I will fix this. This should say 2.714. And then I need to make sure that 2.714 divided by 0.808. I'm going to divide that by 0.808 to get 3.35. So it looks like there's actually some typos here. This should say 3.35. just like that. So I will make these changes, and so we have T crit, that's going to be fine, 1.9. So anyways, the conclusion doesn't change, although the numbers are a little off here. We are going to conclude that the post-test scores are higher because they have a higher mean. So the mean difference is 2.714. That difference is statistically different than 0. So there was an effect of this intervention. Although we can't be entirely sure, but again, that's a matter of causal inference. But it's supporting the idea that there's a causal effect, but we need to use like special types of research designs before we can make those kinds of conclusions, which are beyond the scope of this class. Okay. So I will update this and post updates. So by the time you get this, you will not have those inconsistencies. So assumptions of the dependent t-test. So really, again, two variables, very similar assumptions. One needs to be numeric. Ideally, that numeric variable is normally distributed. The other is going to be a binary categorical variable. And let's say you want to know the difference in test scores before and after an education intervention, then we're going to be comparing pre and post test scores to see how effective the intervention was. So that's an example. And then independence. So although the scores for each pair are correlated, one subject's score should not be influencing anybody else's scores, right? So if I make a matched pairs design where I put the two smartest people in different groups, then the next two, etc., within those pairs, they're going to be like high scores if you're at the high end of the distribution, but still like you should not have like person one should not have given the answers to person two, right? There should be independence in that sense. And finally, we're going to turn the page to SPSS to look at how to do this in our software. So for this one, we're going to be looking at example 2. So I want you to load the data, the t-test dependent repeated exercise. And by the way, I didn't say this before, but look, there's other files here. So SPSS has output. I just generated this by showing you how to do it. So you can load that and you'll see it's the same thing I pulled up earlier. You can also save it as a PDF. And then you can save syntax, which is code beyond the scope of what we need to know as a class. So really the only thing you need to do both of these examples is to follow along in this video and to get these data sets. So I'm going to come to SPSS. I'm on my t-test dependent repeated measures example 2. And here you can see I have 12 people. I have a pre and post test score. And if I want to conduct a paired samples t-test, so remember the book uses kind of confusing language. I'm going to always call this the dependent or the paired samples t-test. They're the same thing. That's what the whole world calls them pretty much. And if we go to SPSS, we go to compare means. We're going to click on the paired samples t-test, literally pairs of observations. And I've already loaded this up, so let me. And then you can put pre and post here, and then I can hit OK. Now, it has conducted the test, but right now it's showing me the data window. Remember, SPSS has 3 types of windows: syntax, data, and output. So I need to switch to my output window. And it's going to give me some interesting statistics here. So pre minus post, and typically we probably want to do post minus pre. That would probably be the better order. It's going to be the same thing, just the negative sign is there. So the post-test scores are about 0.833 higher on average. The question is that statistically significant? So we come and look at the p-value, the two-sided. Oh, 0.044. Yeah, that's below 0.05. So this difference is statistically significant. And like we did for the independent sample t-test, you can come and see how we might report this APA format. So for this sample of 12 individuals, The pretest scores had a mean of 4 and an SD of 1.1, while the post had a higher mean of 4.83, an SD of 1.1. When we conduct our paired sample t-test, we see there's a significant difference between the means of pre and post test scores. The t-statistic with 11 degrees of freedom is negative 2.278, which is associated with a p-value of 0.044. So significant at the 0.05 level. And so that's how we use SPSS to do our dependent samples t-test, right? Pretty easy. And finally, I'm going to wrap up with a couple of last things here. So the first is talking about measures of effect size. So you can conduct a statistical test to tell you whether two variables are associated. The whole limitation, though, of statistical tests is that there's a lot of things that will make them significant, even if the difference in the means are really not that small. Sorry, not that big. For example, sample size is a huge thing here. So if I have a million people in my data set, a difference of like 0.001 can be flagged as significant. Also, if I have a really small sample size, I could have a huge difference of like, say, 5 points, but it's not statistically significant because I don't have enough information to be certain that if I were to do this study again, I would find the means are different. So we're going to complement statistical significance and p-value type decisions with measures of effect size. The great Jacob Cohen did a lot of research on this, and he basically said, okay, it's statistically significant, but is it practically significant? Is it clinically significant? And so the way that he approached this and the way that pretty much how he guided us, and pretty much everyone agrees with this idea, is that we should be using effect sizes to communicate the magnitude of effect. Because remember, statistical significance depends heavily on sample size. That is a huge problem. We get around that by complementing statistical significance with measures of effect size. So for our t-test, we're comparing a binary categorical variable to a numeric, hopefully continuous and normally distributed variable. Two variables. We want to know how strong the relationship is. So the t-test will tell us whether there's a statistically significant relationship between the two, but sometimes that may not mean it's an important difference or a large enough difference that anyone would actually care. So to get around that, we complement our p-values and hypotheses test with effect sizes. And the one that we use for the t-test, it's called Cohen's d. So Cohen's d is easy enough to calculate. It's just the mean difference in the numerator divided by the pooled sample standard deviation. So S sub p, and that is the same SP as we saw here, the pooled standard deviation. So computing Cohen's d is not very difficult, but it's very helpful. And so what I'm going to do is I'm going to show you an example from real published research now. So this is from a dissertation where I actually helped the author do her statistics. She's a great scholar. Her name's Deanna, and her paper is, of course, like any dissertation, published and public domain information. So you can go. I've uploaded her paper to Canvas, by the way, so you can go get this paper and you can go find this table and see how she described it. Although I actually put how she described it in her dissertation. So let's break down this t-table and see what we're looking at here. So her research question was basically, are breastfeeding behaviors related with brain wave frequencies? And I'm no neurologist, so I don't really understand exactly what relative theta, relative alpha, absolute alpha is. All these, I don't exactly know what they are. That was her area of expertise. So I helped her set up the t-test though. So we have a numeric variable. You know it's numeric because look, we're giving the mean and the standard deviation of relative theta power, and I'm breaking down into two groups. ever breastfed and not breastfed. And I put the sample sizes of both groups there. And you can see that I've got the mean of 0.56 and the mean of 0.59. And the question is, like, those don't seem very big. The difference is 0.03. But here's the thing. The Rawls scale of theta power, it's on a really small 0 to 1 scale. So it's kind of hard to know, is 0.03 meaningful or not. You basically can't tell. You can kind of tell if you take into account the standard deviations are 0.1-ish. I would say it seems like in the small category, but it is a change. Like 0.03 is meaningful based on that standard deviation size. But we can make our lives much easier by using Cohen's d. Because Cohen's d will be on the same scale for every single study you ever look at, no matter what the variables are. And you see here the strange scale of 0 to 1 for relative theta power. It looks like it goes from like 1 to 2 for absolute theta power. These are all on the same scale. And so Cohen tells us that 0.2 is small, 0.5 is moderate, and 0.8 is large. So you can see if 0.5 is moderate, you have a few Cohen's d here where they're kind of large in size. And notice that we also have the p-value. So again, we're complementing hypothesis testing with reporting of the effect sizes. And in Cohen's d, look, it's 0.26 is a small effect. Notice it's not statistically significant though, but once we get to 0.45 Cohen's d, highly significant. 0.57, these are way significant. This really small Cohen's d, not significant. So you see how the effect size Cohen's d here for us, when we're interested in comparing the means of two groups, it only communicates the magnitude of relationship. The p-value has this issue that there's a lot of things that influence, not just the difference in the means, but even like, you know, the variability, the sample size. There's many things that affect the p-value. So my strong suggestion is we always complement our p-values with effect sizes. And when we're comparing two means, the correct effect size is Cohen's d. And I will be talking about this paper more in the coming weeks because it has stuff on regression analyses. It shows us how to construct a descriptive statistics table. It does stuff like chi-square test, which we're going to be learning in the near future. So I will be referring to this dissertation in a little bit, but please look at it and read the methods and stuff. And if there's any questions you have, come talk to me about it. I'll be happy to answer those questions. So that is all for this week. Thanks for tuning in, everyone.